This video is about analyzing electric circuits using Norton analysis. Here's a picture of Edward Norton. He and his co-workers at AT&T were some of the first engineers to apply Thevenin's theorem. But Norton worked with recording instrumentation that was mostly current-driven, so he proposed an equivalent circuit based on a current source and a parallel resistor. Any linear network of resistances can be reduced to one equivalent resistance. Norton's theorem converts a complicated circuit into a simple circuit with one current source in parallel with one resistor. When a load is connected to the Norton equivalent circuit, it behaves exactly like it did in the original circuit. That load can be almost anything that consumes power. Here's a circuit with one battery, one current source, and three resistors. Let's call R3 the load and find the voltage and current through it. The first step is to remove the load resistor. I'm going to mark the terminals where the load resistor was with A and B. The next step is to find the Norton current. To do that, we must first short out A and B. Now we can find that current that flows through the wire, or the Norton current. Let's mark what voltages and currents we know. We know that this is 0 volts. If that's 0, this is 10 volts. If that's 0, because this is a short, that is also 0 volts. That means we have current flowing from the battery through the 6 ohm resistor, and when it gets to this point, because there's a short back to ground, it's going to continue around like this back to the battery. And that current, I1, is equal to 10 minus 0 volts, or 10 volts, across a 6 ohm resistor, which is 1.67 amps. So the current that flows here is 1.67 amps. Now this is a 2 amp current source. That means we have 2 amps flowing into that current source, and we have 2 amps flowing out of that current source. This 12 ohm resistor is in the path of that 2 amps, so 2 amps also flows through it. Kirchhoff's current law says that all the currents entering and leaving this node need to be the same. So if we have 1.67 amps flowing in and 2 amps flowing out, we need to have another 0.33 amps flowing in to balance it out. So we know the current that flows into that node here is 0.33 amps. That's the current that flows through AB. That means our Norton current is 0.33 amps. The next step is to find the Norton resistance. To do that, we remove the sources and replace them with their internal resistance. The battery has an internal resistance of 0, so we'll short that one out. The current source has an internal resistance of infinity, so we'll leave that one open. If we observe carefully, we see that the path from A to B is broken here, so that's an infinite resistance along this path to B. If we look along this path, we see that it's only 6 ohms. So 6 ohms in parallel with infinity is 6 ohms. The last step is to reattach the load resistor and find the load voltage and load current. The load resistor was 4 ohms. The other thing we have to remember is that the current here went from B to A. That means that this arrow is backward, and the current is really going to flow in this direction. The 6 ohms and 4 ohms are in parallel. So that resistance, the equivalent resistance, is going to be 1 over 4 plus 1 over 6, all inverted, which is going to be 2.4 ohms. And if we have 0.33 amps flowing through 2.4 ohms, that voltage is going to be 0.33 amps times 2.4 ohms equals 0.8 volts. So our load voltage is 0.8 volts. But not all of this 0.33 amps flows through the 4 ohm load resistor. Some of it flows through the 6 ohm resistor. In order to get the load current, we need to take 0.8 volts divided by 4 ohms, and that gives us 0.2 amps. Okay, now it's your turn. Make R1 the load resistor and find its current and voltage. Press pause now and resume the video when you think you've got the right answer. Let's see how you did. Step 1 was to remove the load resistor. Step 2 was to short out the gap that was left by the load resistor and find the Norton current through it. In this case, the current flows from A to B and it's 4.5 amps. Next, we need to find the Norton resistance. So we replace all of the sources with their internal resistance. The battery is shorted out and the current source is left open. When we do this, we discover that there's only one path between A and B, and that's through the 4 ohm resistor. So the Norton resistance is 4 ohms. Then we reattach the load resistor. We find the voltage across it and the current through it. In this case, the current is 1.8 amps and the voltage is 10.8 volts. And there it is marked on the original circuit. We can check our answer by using Kirchhoff's voltage law and current law. If this is 0 volts, then that's 10. If we drop 10.8 volts, that's a minus 0.8 volts. And this is 0 volts here. The 2 amp current source forces 2 amps to flow through R2. Since we have 1.8 amps entering that node and 2 amps flowing out, we have to have another 0.2 amps flowing into that node to balance it out. This causes a voltage drop in this direction of 0.8 volts. As we go around the loop this way, we go from 0 to 10, we drop 10.8 to minus 0.8, and then we increase 0.8 back to 0. Since it satisfies Kirchhoff's voltage law and Kirchhoff's current law, we can be sure that we got it right.